Hi, and welcome to this session on live reloading of microservices on your ESP32. I'm Kasper, the co-founder and CEO of Toit, a startup company in Denmark focusing on building the next generation software platform for IoT. My background is within the fields of software engineering. In 2006, I joined Google to help them build the Google Chrome browser, and I focused on the JavaScript engine inside, making that approximately 100 times faster than the competition at that point in time. Having worked for a number of years on the web in context of Chrome, I started a language project called Dart that is now the basis for a mobile application framework, Flutter, which is taking over a good chunk of the mobile app space globally as we speak. Dart is a language that I helped design and implement, and it's something that's powering a lot of next generation mobile applications. Having worked for a long time at a big American corporation, I wanted to stand on my own feet. So in 2018, I started a small company called Toit with the goal of making a vastly improved experience for developing functionality for devices. The whole founding team for Toit actually comes from Google, and I feel very blessed to work with some of the best people in the industry, and together we have decades of experience implementing some of the most used software platforms in the world. Our focus has always been software platforms, and in particular programming language implementations and virtual machines. So that's sort of the governing principle of the work we've done. A virtual machine in this context is typically like a runtime environment for executing programming languages efficiently, and that's been the focus of our work for a couple of decades. You probably know VMs already. They power servers and desktops and mobile systems, and platforms like the Java platform or JavaScript in the browser or Dart in a Flutter context are all powered by programming languages, Java, JavaScript, and Dart, and they're implemented by means of a virtual machine that runs on the hardware. In 2018, we thought, why don't we try to use the same techniques, this virtual machine concept, on network-connected microcontrollers like the ESP32. We saw that the ESP32 and chips in that family were powerful enough to actually be very meaningful small little computers in their own right. So they needed, at least in our perspective, a richer and better software platform on them to help people be more productive and to raise the abstraction level on these devices, making it easier to build better stuff quicker. So we put the Toit VM on an ESP32, and we made it so that you can run independent applications protected from the virtual machine and the underlying hardware, and gave them a sort of a feel where they feel much more like small little containers and isolates in their own right, things that run side by side and are independent, instead of having this sort of classical monolithic approach to these things. And if you look at that thing and think about the architecture that sort of implies, it looks something like this, right? On a traditional stack, you compile and you link all the system functionality together, maybe on top of a framework like the ESP32, and you call all of that firmware. This is what you'll update. This is what you'll ship to your customers, and this is what you will be concerned with. So the thing is that when all system functionality is compiled and linked together that way, dealing with it and introducing new functionality in these things become slightly more problematic than you'd like, because a change in any part of the system is essentially a change in all of the system. Now contrast that to the architecture that we're proposing with Toit on the right. We still base ourselves on the ESP32, but we add our virtual machine layer right on top of that, and that constitutes our firmware, you could say. On top of this firmware, we then have individual applications, pure software, that run in isolation from each other in their own little containers. The right-hand side looks much more like what a modern operating system would look like, whereas the left-hand side is more sort of the traditional real-time operating system structure. We feel that for lots of software developers, having better modularity and better tooling is a big win. So we focus on that right side of this. I think for me at least, the key point is really that the VMs, they, in addition to giving you isolation between these components in our case, they also give you what I call serviceability. The ability to actually install and configure and deal with the software on your device at runtime, whether that device is in production or in your lab. So this ability to actually service the device, change what it does, maintain it, look into it, and understand it well, I think is really, really key. And most real-time OS-based systems sort of stop at perhaps at observability, where you can see what's happening, but you have very, very few means for actually manipulating and changing the software that runs on it in production. So the focus for this presentation will actually be how you can start using Toit on your ESP32. And I want to just go in there and just tell you how that would work, to give you a sense for what it is that we've built and why you should care. So I want to show you how you can get started using Toit and higher level abstractions on ESP32. And it's surprisingly easy to do. It does not require anything fancy from you. So I'll try to go through how the structure of it works and show you in practice how you could get started. First up, Toit is an open source and free project. It comes with a language implementation on GitHub and a package manager that allows you to reuse functionality built by others in a very seamless manner. These are the two sort of core components of what it takes to run Toit programs. But we found that actually building a developer-friendly tooling on top of this is essential for making this very, very accessible. We call this Jaguar. It's an open source developer tooling based on Toit, and this is the easiest way to get started with Toit code on your devices. So the way you would start this, and I'm going to show you this in a moment, is actually just downloading and installing Jaguar. It's very well bundled up, so it's easy to get going with that. You can use Homebrew on macOS, Winget on Windows, and on a few Linux versions, we've also sort of packaged up an easy to install version of this. If you are not running one of those platforms, of course you have the ability to just go download the prepackaged builds from archives from the GitHub repository. But it's not super interesting just to see these words on the slide. I think it's much more fun to dive in there and see how it works like. So let's try it out. I'll be installing Jaguar on my MacBook from the terminal. So first up, Jag is not installed, so I'll pull it down using Homebrew. I point Homebrew to the Toit line/Toit tab, and it installs it from there. Having installed it, the Jag command is now available for me, and it's installed version 1.6.6. Now I'm ready to actually put the Jag firmware onto my ESP32. I've connected the ESP32 using a serial link to my MacBook, and I'm going to use the Jag flash command to actually put the bits there. Jag flash needs a few supporting tools like the ESP tool for it to function, so I'll download those using Jag setup. When Jag setup is complete, I have a fully functioning Jag installation, and I can flash the firmware onto the device. The flashing uses the ESP tool that you might be familiar with, and it is actually the last time in this presentation where I'll be flashing and putting functionality on the device using the serial link. The rest of the presentation will be using Wi-Fi to put new code and new functionality onto the device, so we don't have to wait for the serial link, and we don't have to use the ESP tool going forward. Now we're done putting the firmware onto the device, so we can do a Jag monitor and get the serial output from the device just to see that it seems to be functioning and connecting correctly to the network. Every Jaguar device gets a name by default. In this case, we've decided to call it upbeep mail, and we'll be using that name in the next part of the presentation to identify the device and make sure we're talking to the right one. To actually do coding on the device, I find it practical to use VS Code, as it is an integrated environment where working with source code and getting completions is a helpful thing to have available. So I'll start up Visual Studio Code, and I'll have a main.toit file. Now to work with Toit code, I advise you to install the Toit extension, and you can find that in the Visual Studio Code marketplace, and you can go install it from there. Now having installed that, We actually have a fully fledged environment for writing code with code completions and everything. So we'll do a hello world example like that, and we'll be ready to actually run this code on the device. Now, to actually run the code on the device, it is really practical to be able to see the serial output from it. So we can start Jaguar's serial monitoring and get that on the right port right here within Visual Studio Code. You see this down here at the bottom of it. You see we're still talking to upbeat mail and we're ready to actually run code on it. Let me split the terminal here. So the left part will be the output and the right part will be where I engage with the device. So now let's try to run main.toit on the device. Jack run main.toit is all it takes to actually get to choose upbeat mail and send the code, the hello world example, to the device. You see the output here in the serial. And what's happening underneath here is actually that we compile the code, send it, install it in Flash, run it, and then stop the program again. So quite simple to use. We can print more things than just hello world. So we'd say, let's print the time. Time that now returns to the current time. So we might be able to just get a sense for that. Apparently my ESP32 believes the time is 1970, but this allows me to actually illustrate how you can pull down a supporting package like the NTP code for using the network time protocol to update the time on the device. So we'll do jack pkg init to make this repository, this directory that I'm working in, a place where you can install packages, and then we'll go install the NTP package right here. We've installed it, and now it's actually available for use. I can import the NTP code like this, and I can start using it. Now the NTP synchronize method, we can go to the definition of that to see what it does. It returns a result, an NTP result, which is an adjustment and some accuracy. So I'll be using that to actually update the time and get a better sense of what time it really is than in 1970. Let's go back again. So let's try to actually do the synchronization here and then print out the adjustment that NTP believes we should be making. Like this. We'll run it again. Jack run main.toit, like here. And you'll see that the output reflects that we should be doing a rather large adjustment to the time, like many, many minutes. So let's try to do that. We'll import the ESP32 support code, and that allows us to actually adjust the real-time clock with the adjustment, like this. Run it again. No restarts of the device, no nothing. We just run it and see that now we've changed the time, and we're now in 2022, which is much, much better. So we can clean this up now and have a nice working example that adjusts the time based on this. We'll be using a more structured logging mechanism than just printing. So let's do like a logger is like an ordinary logger with a better name, with name, we'll call it NTP. And we'll be logging some information like log info. And we'll be doing like, we'll be telling ourselves that we're synchronized and that the adjustment was the sync adjustment. And that the time now is the current time. We can run this just to get a sense for how it works. And we'll see that the output is now NTP info, synchronized, the adjustment was made, a couple of milliseconds, and we have a new updated time. Now with that, let me return to the presentation and tell you all about what you just saw. So what you just saw here was like the Jaguar experience that shows you how to run Toit code on your device. Now, Toit is a language and an implementation of that language that's open source. We've built it to enable high-level programming for microcontrollers such as the ESP32, but it is a custom programming language, so I think it's worth spending just a few minutes on explaining how it looks like and just walking through a little bit more of the context for it. So simple programs should be simple to express, and we've done our best job at making this very lightweight feel. So the hello world is something you've already seen. Looks like this. Of course, you can have functions, and you can introduce abstractions over expressions and statements like that. And then here I have a few examples of a function that returns the square of an x, and a function that returns the double a given x by adding them together. I just want to showcase that functions are easy to write, easy to type with static typing if you want to, and in general, it doesn't feel like a very scary thing to enter. The arrow is a way to indicate the return type of a function, and we like that the return types are given sort of at the end of the signature of this method, much like many of the modern languages out there. Clearly, you also need access to things, and we're going to look more into this later. Things that are like lower level. So Toit comes with pin level access to I2C and GPIO abstractions, and makes it straightforward to work with these things. Here you see some of the named arguments come into play. SDA and SCL are not just two positional arguments, but they're actually named, and it's understandable what they're doing. Toit is certainly not unique in the sense that it's the only language that has these things, but we feel like it's a nice and fresh take on what a modern language looks like in 2022. So having sort of just seen the language, seen it a little bit in action, I want to just go back to some more real code and show you how we can combine some of the simple stuff we did with Hello World and NTP code, and show you how this concept of live reloading fundamentally changes how you want to work with your code. So live reloading is pretty simple. It just means that we will use the fact that Toit is fast, and we will rerun your program on your ESP32 whenever it changes on the disk. So that means that if you're sitting in your IDE, VS Code, and you're changing a file and you save it, we'll compile it, upload it to the device, rerun it from the start. And that really works because it's always possible for us to stop a process in a clean way and restart the program again later. So all the resources are reclaimed the right way. So having a stack that allows you to stop things when you want to and restart them, and having it fast enough that we can actually get away with just watching and rerunning whenever things change, means that you have a super powerful way of learning quickly and building cool things. I'm going to show you how you can hook up a BME 280 sensor without knowing too much about the BME 280 sensor in a live way, where we just go to the code and we'll try adapting the examples we have to make them actually use a BME 280 sensor that's already connected to my ESP32. Before we dive into the live coding, let me just store the main.toit file here that we created as an ntp.toit by just copying it so that we have it for future use. Now with this, I'm actually ready to just start running this code and having the file watching take care of all the compilations behind my back. So I'll use Jaguar, watch for changes and rerun, and I'll tell it to do this on Upbeat Mail, and you'll see here that it's actually starting up, scanning and running some code on it. Now if we go back, we can tell that it actually ran this just again, got a little bit of a new NTP information, but now behind the scenes we actually have an instance of Jaguar running, watching our every move, watching what we're doing with this file. So if we start changing it, simplifying it, and saying let's just do some printing, go back to Hello World again, and we save this, you'll see that it prints Hello World. And if we want to try something else out in this context, we can just do it. Hello ESP32 fans. I save it, and it immediately just runs it on the device. So this is great for trying things out. Now I actually connected a new sensor to the ESP32 here, and we might be able to just use some of the I2C and GPIO support to figure out which sensor it is. So let's stop importing all the logging and NTP stuff and just import the I2C library and the GPIO library. With those in hand, we can actually construct an I2C bus based on some GPIO pins, 21, and CL is going to be 22. This is how I wired it up. And we can try to print the result of scanning the bus for devices. Now I just saved it, and we can see there it still says hello ESP32 fans, and it prints a single device 119, which is a BME 280 if I'm not mistaken. So let's try to actually pull down the BME package, and we'll do this by calling jack pkg install BME 280 down here. And this will give me some helpful extra driver support for the BME 280. So if I do like this, import it, we could say print is it BME 280, and then just print bus.scan if that set actually contains the BME 280 address. And we just save this, and it will tell us right here, is it a BME 280? It actually says false. It's probably because I need to use the alternate address. I'll save it here, and we'll get, is it a BME 280? True. That's great. Now we can actually use the I2C address alt here to construct an I2C device. So we'll do I2C device of this address, and we'll get something we can use. It's actually going to be called on the bus like this, so that everything is set up the correct way. So with that, we can say create device, just to check that we actually have this device created. It says create a device, that's good. Let's do a driver then based on the device. So we'll do BME 280 driver device, and we'll say print driver created something about the temperature, driver.read temperature. I'll save this, and we'll see that it's at 21.7 degrees here in my house. But just using the watch functionality, we've been able to just quickly code up something that uses a BME 280 driver, constructs the right things, tries a few things out, and figures out how to get the temperature out. I think that is a neat way of working with code on a device, like live reloading of the code while you edit it, so you get a sense for what it's doing. We can clean it up a little bit and say, actually, the temperature, we'll pull it out here, Celsius, right? So we'll do like this, driver read temperature, and we'll just write that it's actually Celsius. And we'll do Celsius here instead. So with this, small modifications, refactorings, we've made the program better, and we've made something that actually reads the device temperature from the sensor, and gives me that full view of how the code is going to work on the device when I run it. Okay, that was hooking up a BME 280 sensor using live reloading and file system watching. Now, I don't think we should stop there. I think we should go even further. And once you have a way of running code on a device, it's a very natural thought. How can I run more code, more independently compiled and develop parts of the system? And this is where microservices sort of come in. That the ability to build your firmware out of modular services that can be installed and upgraded independently is incredibly powerful. And this is another thing that's very clear in other parts of the industry, that a great way of decomposing applications and making them more robust by giving them cleaner interfaces between smaller things is, if not overdone, a very powerful mechanism for writing better and higher quality code. So I've shown you sort of the architecture for this already. We have the ESP IDF at the core, and we have a virtual machine just on top of it. And then we have this ability to have multiple applications or services running on top of this. So the way we actually map this to something that Jaguar supports directly is by taking these different apps and installing them with Jaguar in a live way on the device as separate small containers. So to install the NTP code we already saw, we could just say jack container install ntp.toit and give it the name time. It's a time synchronization container then. And that gives us a way to just say, I already built this. Let me just take that code, stuff it in a container, and have it run. And with Jack, it's as easy as that. whenever you then reboot your device, it will rerun this code. So it's now installed, not just a transient thing. We can do the same with the BME 280 code that we have, so that whenever you boot, you get a new reading. And clearly, you can also have a separate application that does your main thing, and have them just installed side by side. And once you've done that, you can ask the device to like list whatever is on the device and just go through that. So I think I want to show you how this works in practice. So I'm going to jump into VS Code again and just give you a sense for how this actually works when you try to build functionality out of multiple things. Now let's start with listing the containers already installed on the device. You see them down here, Jag container list. There's only one, it's Jaguar. But we could go install the NTP code that we built as a container. Jag container install. We would call it time and base it on the ntp.toy file. Now we're installing this on Upbeat Mail, and you see that it says info container time installed and started. Good. We can list the containers, and we'll see these two. We just adjust the split here a little bit. Okay, so we now installed the NTP code as a separate container on the device. That container will actually restart whenever the device restarts, so it will always be present and functioning. Let me try to reboot the device by resetting it, and you see it starting the time container just before it connects to the network and starts running everything. It actually does the synchronization, and we actually have a working time here. So you see that we can compose the functionality of the device from independently compiled and built services that run in their own isolated container. Pretty neat. Now, if we were to do something like that with the BME 280 code and the main application that prints the temperature out, what we could do is we could copy the main file to bme280.toy, just so we have a copy of it floating around, before we start changing the main application here to be more independent of the BME 280 driver and just capable of using any kind of temperature sensor. So let me just start dropping some of this support for the BME 280. And instead of using that, I'm going to pull in a small package of sensor APIs, and we're going to use the temperature one in there. It's going to be sensors.temperature service. And we're going to construct a client for accessing that service from the outside. And with that in hand, we're going to change all of this code to just say, give me the temperature service, and let me read from that. Now, when I save this code actually still is being watched by Jaguar. So we'll run this code on the device, and it'll actually give me a nice little error here. I cannot find that service. There is no temperature service on the device. Now, good thing I preserved the bme280.toy file. We'll go into that, and we'll change it from being just a piece of code that prints the temperature, but instead be something that will actually expose this sensor service to the other application. It's pretty straightforward. We still need I2C GPIO on the BME 280 driver, but we also need to import the sensors library here. But in this case, we're going to pull in the helpers for defining new sensor services. We're going to extend that and create a BME 280 service that extends the definitions and the temperature service here. So we're going to use the driver, the BME 280 driver, to build this. We're not starting completely over. And we're going to create a constructor for this thing. It takes the driver and tells the superclass that we are the BME 280 service, and that our major version is, let's say, 0, and our minor version is 0. Or 1. Let's call it 1. Now, with the BME 280 service, we're actually missing a single implementation of the read functionality, but that's easy to do. Read float is just calling the same thing on the driver. Read temperature. So with that, we now have a BME 280 service that we just need to install and have running. And then hopefully the application that we were building just before will use this without knowing that it's actually talking to a BME 280. So instead of printing in here, I'm going to do the service, BME 280 service from the driver. and I'm gonna install it. So now I've written this thing. All I need to do is to actually put this BME280.toit code in a container on the device, and hopefully that will make it available for the main app. Let's go down here again and say jack install. This time I'm gonna put the thermo, and we're gonna install the BME280.toit file. So we see over here that we've installed the thermo app and started it. So let's go back to the main thing and just try to do a trivial change to it and see if that reruns it. What you see now is actually this program starts and it prints the Celsius 2196 without knowing that it's talking to a BME280, without knowing that it's actually calling into a service defined in a different container. It still gives you the right answer, and it gives you this complete freedom to couple and decouple your functionality in the right way. Okay, good. So you saw this in practice. The way the BME280 service and the application in main.toit actually use each other is by means of remote procedure calls. So they actually communicate by sending requests and sending replies between these two independent applications, two independent containers on the device. And that approach is probably recognizable from higher level and larger systems. This ability to actually have independent isolated components that still communicate over well-defined APIs, sending and replying to each other through a messaging protocol. It's done in a way that's fast, but it's also done in a way that's super practical. The combination of these things, live reloading of code on your device, installation of containers that are separate but still connected, and the ability to write high-level abstractions in your code makes for a really awesome experience. I wish you all would try Jaguar today and build better things faster. We think it just might be the best open source high-level language and tooling for ESP32 that's available today. But don't take my word for it. Go try it out and build something awesome. Thank you.